Testing, testing. Testing. Okay, guys, welcome to Saturday night, whatever this is, Friday night. Okay, let's jump into this. I'm going to the report again. Denny Pate's report, as reported by the photographs. I think this was FDOT reported these photos. Yeah, FDOT reported these photographs. I want to show you a couple of things that are very important. Could possibly create these top spalls. He thinks these top spalls are isolated by themselves, not that he thinks they're spall. It's just spalling. I just find that amazing that he could think that's spalling and it's still connected here. You know, that they're spalled away here and here. Now, I might have said something about spalling when I first saw these images, not this current batch, but we only had the rest that we had left. I kept saying there might be some steel conflict in here. But we're going to run a couple of things real fast. All right, so these are these images again. This is a top view, so if we're looking down, we'd be able to see the X-ray vision eyes, we'd be able to see the shims or the blue, and that's the ended up pylon, the back of the bridge, so FIU Bridge. And I can't load up, I cannot load up the report again. It won't load for some reason. The back of that pylon right there. I'm going to grab the image for you. A better image, perhaps not. Well, let me grab a better image, but I'm just looking at it. There we go. We'll go back to that one. So this part right here sticks out. It's 1 foot, roughly. But Denny Pate's going to talk about a distance of 4 foot and some change. He might be talking about the edge of the deck to here, or he could be talking about from here to here. Nevertheless, the last transverse post-tension rod goes, post-tension tendons come across right about where this pole is, across the outside the diaphragm. So it's 2 foot in, and that would be the face of that guy coming across. So right here, that's that diaphragm that you're looking at, the intersection of 11-12 node. I'm sure that's it. I feel confident. Let me see. Yeah. Feel confident that's it there that we're looking at, 11-12. Here's 4 foot, 1/2 inch to the center line of the post-tension tendon. There are none here beyond that in the diaphragm. Go to the report again. You have 2 feet. See, that's 2 feet. Bounce back again. So this line lines up with not counting the little bump out blister or the part of the deck that sticks out. He totally was winging this, and I don't know how they made a report so nice within that short period of time. It only was out there 1 hour. Here's 1 foot here, shown 1 foot here, and it clears this. So how do you measure this? If you got your 1 foot mark beyond the bridge length, it's not measurable. You got your dissecting line, not dissecting any part of the bridge. So it's not even saying plus or minus. So I just find this drawing to be very odd. But let's go to very odd in its representation. It is unclear how a change in distribution of the contact pressure on the bottom surface from being supported like this for several weeks to being supported at the bottom on the 4 shims could possibly create these top spalls. Now, Denny Pate, Linda Figg, and we're going to do the evaluation of a bridge in Massachusetts, Arrigoni Bridge. So Arrigoni I did that video on that already, right? Let me try that. This bridge here. Denny Pate's going to be doing the right 30.94 million state funds slated for Middletown Bridge, June 28th. All right. So I'm following up on this. I've already got the attorneys in Connecticut and everything calling me, contacting me and calling. They're going to give us, we're going to have a lot of data on this bridge to work with. We're going to go back 10 years if I can, if they release the data that I'm asking for. We're going to go back 10 years in reports to see what the structure is doing. I'm not sure if I should tell you what part of the email, so I'll bounce around it. But I'm not sure if it wasn't said in confidence. You know, the attorney didn't say this is in confidence. But I felt like it was telling me something in confidence. So I don't want to be the first to toot my horn about this because I think it might have been said in confidence. But so I'll just say that we still have to wait, and I'll share it once I get the data. Then I'll share it. What I'm holding out on. We still have to wait to. Yeah, I'm going to not be able to say it. Let's move on. So Denny Pate is getting the $40 million contract there apparently, and apparently. All right, so how's that? I'm allowed to say that. Apparently, he's getting the $40 million contract. Linda Figg, Denny Pate, and yet they can't evaluate their own bridge with their software and everything else. I mean, I don't know. I don't get it. I mean, I get that. I do get it, really. I find it hard to believe that a guy with that skill set also doesn't have ability to evaluate structural cracks in concrete, his own design. He doesn't have the ability to see that this is lifted up and not just falling off, that it's up and that it's still attached to the structure here. So it just can't be spalling. The whole thing is taking an action, the whole number 12. Let's go ahead and prove some of his beautiful software. I have to say that it's very interesting. One of the questions I keep asking, and now I'm going to state that this is the answer. I keep wondering if it was fully supported. Well, based on this statement, I state now that with some surety based on this, is that this was fully supported. And the difference is it did go to the shims at this point. So I don't have as-built. They won't give us as-built, but I got declarations, statements of me, and these statements are stating that now it's on these shims, and here they're not talking about being placed on their own shims. So this appears to be fully supported. That means that this number 12 has a full base underneath of it. Whereas we know at the bridge collapse on this 12 overhangs, cracks like hell. Let me try that. Oh, I can pull up my own damn video that would show it, but really, let me get the timeline corrected here. Let's see if we got something. Wow. It's something else, right? Cracks like hell don't show up. That's interesting. Let's go back to tools. Let's go with past month to see if that works. And let's go anytime. And let's just get rid of that. Oh, cracked like hell. Let's try that. Okay, here we are. So here are the images and that's what he's calling spalling. Yeah, that there's no reinforcement behind here to help this spall. So there's another force that created this spalling, this effect. Hey, George, my cat. And this one, though, these are the cracks. Let me zoom in for you guys. These are the cracks here. Now watch when I go back. These cracks go this direction and this direction. Now let's go to the report again and his software that he used. And I've got to scroll up a couple of, here's the software. Let's go a little higher than that. Right. Several different loads and load combinations were considered to understand both total state of stress and effects of some individual load components. See, this here is the problem. This artificial intelligence is how they're doing their evaluation. And that's just, you know, artificial intelligence can't think. All right, it just can't think. It can only process. So here it appears to be the three-dimensional finite element evaluations: total self-weight, stress changes, and stress change from stresses or slackening the post-tension bars in number 11. Take very, very significant note of this. So I tell you, people can't lie. You just got to listen to them. They can't lie. What is the giveaway here? Slackening, or was it detensioned? So obviously there's some conflict in his statement. If I were to be questioning him, I would say, what is your definition of slackening? What do you mean by slackening? Is that the same as detensioning? So slackening clearly does not mean detention. That means take off some slack. Give me some slack. It's still under tension. So this is kind of a giveaway for me. And remember, I'm biased though in that statement. So I have to, you know, please let that be known. Total self-weight and all post-tension transfer longitudinal post-tension bars. Transverse longitudinal post-tension bars. Everything was done on that one. All right, so watch now. Let's go to this thing. Stress changes when placing onto shims. Placing onto shims. When the span was placed onto the shims, are the stresses on the diaphragm essentially equal on the north and south faces, or is one of the face more highly stressed? It's the question he puts here. Yet this is the diaphragm that his software, and he's not showing the other end. This appears to be 12 here, and this is the shim then, as we see here, 1, 2, 3, and 4. Okay, so take note of the stress here. We're going to come to that. But look, see this shape? This is the software saying that we would see red here, and very importantly, it sees red all the way out to the base of that nodal area. That area there, that 12, the overhang, I need some damn images. My cat's ready to go to bed. He's sort of sending me to bed now. That's great. Hopefully there's some more images than this. Yeah, I can't pull up the damn images. Hold on, let me go back one more. And then one more. Let's try the Miami Herald. Maybe they have some photographs of the report. Old photographs. Old photographs. All right. Yeah. So that's that part that's elevated that I've talked about in many of my videos about how this is higher here, back here than here. He's just referring to this as spalling. Just as spalling. He doesn't see the elevation changes clearly, or perhaps he does. And, you know, they make up this report. Get the advertisement. So then we get these cracks like this. This is the same as this here. But we're not done with that. We got another side to it. The results indicate that the stress changes on the north and south faces is relatively uniform when the load is transferred to the shims. Relatively uniform, meaning it's symmetrical. All right, so the cracks are symmetrical. He does not know what the cracks are. He makes that clear at the end of the report. Total stress went on shims. So now this is a weird thing. Total stress when on shims. So this appears to be when post-tension bars are still in place. The number 11 is post-tension, and we're looking at the stress balanced out. Let's look at this again. So now this would be with the remove. It's not. It's a. He's calling that shims too, but obviously that's not shims. And this red up here will help us identify in a moment. So let me go down to using a software. Diagonal crack pattern. Okay, talking about the diagonal crack pattern. Both the hand calculations and the 3D volume elements above concur that some cracks of the nature photograph are possible. Well, we know it's damn near not possible. It happened right here. These are the cracks here. It cracked like hell. Those are the cracks there. No, we'll take it. We'll take that one still. Got a little more clarity anyway. Those are the cracks there. Going back to the report. Why the cracks did not develop in the casting area is likely related to having substantial portion of the load carried in the center. Is likely related to the having of a substantial portion of the load carried in the central area. I don't know what he means by carried in the central area, but let's use it literal and state that the cracks are from the center of the area, the vertical upright downwards. So, Luna, Widow's Peak. Hello, Luna. I hear you. So no, interesting, Luna, what you just said. Having a smaller cracks width of the permanent exposed face is preferable when compared to the other to be embedded diaphragm face. All right, so of course it'd be preferable if they were just spalling. It's unclear how a change in distribution of the contact pressure on the bottom surface from being supported like this for several weeks, unclear, and yet he's producing a document that says how he's going to perform, how he's going to go forward. It's unclear. So why are you going forward? And all his calculations, let me come back to that page. Right? Page marked off, page 39. All his calculations are assumptions on the structure without knowing why the cracks happened. So if you come up here and you do all these calculations and run them, they drive you crazy. It's all on an assumption that no cracks are present, that they're all fair game. But then also contrary, he states how it doesn't meet FDOT's minimum cracks that we must be addressed, therefore must be addressed. He talks about the this area here, he puts it in quote, calling it a node now, and there's a red line, it appears here and here, it looks like this, red line coming across here, interesting enough. The total node must remain attached to the diaphragm / deck, this area here, in order for the longitudinal tendons to capture the longitudinal force component of the strut. So this is where the failure happened. What I've always stated is that if this doesn't stay intact, the transverse tendons fail. The longitudinal tendons fail, rather. And there it is. There's what I've been screaming all along. He's stating it right there. If this fails, then the longitudinal tendons fail, because this load's coming down 12. Okay, the vertical weight. The total node must remain attached. This node must remain attached. It can't fail in any capacity. in order for the longitudinal tendons to capture the longitudinal force component of the structure. I'm starting to see a bending moment in the diaphragm based on his statements too, and he talks about bending moments. But this is the vertical. This is number 12. Nodal shear transfer of vertical loads, factor shear demand, reduced capacity, factor. This is a factor that he's using here of 0.9. So it's not fully a 1-to-1. Easily okay, he's stating, based on the loads. Again, but the cracks, he doesn't know why they're there. So those don't count. And, he runs his compressor strengths and all this stuff with the concrete and comes up with everything that's okay based on this and that. It's further up. He discounts here. He gets to take away the nominal shear resistance of the interface plane shall be taken. Also, the cohesive term shear friction equation is ignored right here. They take off the shear friction that the OSHA report didn't like being deducted. There we go there. And he discounted the post-tension bars as part of the shear resistance, which in this case, it would work in your favor if you were trying to figure out what's wrong and you didn't want to count them. This actually works at making your calculations have to perform even stronger because you've removed post-tension bars as consideration. And mild steel is mild steel is just a structure without post-tensioning. And there's a diaphragm, 2x4, 8 square feet. The shear from the two shims on one side is approximately 476 kips. Nodal shear transfer of vertical loads. Here it is right here. He's talking about the vertical loads, number 12 down. And that's 476. So he's talking about number 12. This is 12. The vertical loads coming down here being approximately 400. At this point, he says 476 kips. I think he changes it to 500 at another point. Thus, the average shear stress on the vertical load is approximately 60 kips a square foot, which is within normal range of 8,500 PSI concrete is what that amounts to. So the this is per square inch. You have to realize that per square inch. So you do that by 144. Sorry, my brain was somewhere else. 144 to determine your total footage, what it comes to. And over here, he did square foot. So you can see how that equals, can get to that easily. You're, at 100 of them, you're at 80,000. So you can see right there at 100. And so it's approximately 140,000 pounds a square foot, what it comes out to. And this is only 60. If I got that right, you just heard it off the top of my head real fast for you. Couldn't find A here. A drove me crazy trying to find A. My eyes looking at this magnifying, I'm like, I couldn't tell. So I thought it was useless. Again, there's his factor. He likes using the 0.9 factor. Compressive strength. Yeah, the A. I can't read this. So I spent a little time playing with it and I bailed on it. All right. As previously noted, bending beam theory. So this is what I went back to the report, and this is what I've been screaming, that it's consider it, I said, a girder, a diaphragm girder. Well, he's calling it a beam theory. I love that. There it is right there. And I was calling it girder. Well, I guess that would be, it's the same as saying girder theory, beam theory, same thing. So this is talking about, this amounts to talking about the forces from 12 down into the diaphragm coming in that direction. And this is what we're looking at. And I went over his tension and compression and all this stuff. It was not interesting because he states, making it clear, he has no idea where the cracks came from. So, and how are you evaluating and making all these numbers up if you don't know how destroyed your structure is at this point. This is taking in consideration that the structure is still sound. So how can you even do these calculations? It's not possible. You can't do calculations on a broken arm. All right, bending check, beam theory. So this is the beam theories. I believe this is what he's implying, is that this would be the beam, the diaphragm now, and the span is from the over top of these shims and extending overwards. So it creates a moment. And this one says, I can't read it. I can't read it, but it appears to be his moment in a positive direction. Right. In a negative direction. As previously noted, the strut and tie method is more applicable to, so the strut and ties up here. It's he gets kind of crazy, because here it's talking about showing the cracks and talks about them. And I don't know if they've read, if he's implying, because it's very short here. Are they implying that that this is a tension in this direction, which is what, a pulling in this direction? Is it the moments from here pulling from here that creates that torque of the number 12? I mean, they don't really. He's vague on that. He's not talking about it. I can't figure it out. Here's 475 and 475, and he's using LRFD 5.63 to justify his actions and his evaluations. But again, this is all broken up, so it's a wasted energy. Now let's go back to that page. I think it's 39. So what's the point of doing all those you make it clear, point after point after point, which is very amazing. Vertical loads. You're talking about vertical loads. Let's go to that damn beautiful software he's using, that the bridge didn't collapse yet. So he ran the software and said, look, I want to know what it looks like if we remove the post-tensioning and number 11. And watch what the software shows. So shear stability, the total node must remain attached to the diaphragm deck in order for longitudinal tensions to capture the longitudinal forces component of the strut. So I find that amazing. So that it must remain intact, this whole nodal area, but yet your node's failing because you detensioned 11, and that would be 11B, and then you get the failure. And even your own software is saying it, but he just dropped the ball. And now this guy's, their FIGG is going to get $40 million to work on this damn thing up there. Well, I can't give away everything that I was written, but you know, I will say that's yet to be determined about that. Okay, where's the damn salt? That was it there. One more red one. So this is what he says. And therefore there is no safety. And therefore there is no safety concern. And therefore there is no safety concern relating to the observed cracks in minor spalls. That's the conclusion there. But we're still going with conclusion. Dimensional finite element, 4 shims located. Okay, here are the 4 shims. This is where the post-tension bar is. Transverse bar. And then we come here. And we, 39. All right, so that was the underside I showed you a moment ago. That's the underside of the 4 shims being balanced, I believe, with the post-tension bars A and B and number 11 tensioned up. Diagonal crack pattern. The diagonal crack pattern we're referring to are these, I believe. Here and the symmetrical side of it on across 12, on the other side of 12. Further stating, both the hand calculation and the 3D environment's right. Why the cracks did not develop in the casting area is likely related to having substantial portion of the load carried in the central area. So I believe that's that number 12 coming down, but I have to leave open. He could be talking about during transportation, but I doubt it. Or in general, the whole load's being carried down the central area because by default, that's where it's being carried. The damn thing's in the center of the bridge. Having the smaller cracks width on the permanently exposed face is preferable when compared to the other to be embedded diaphragm face. Okay, so he's okay with the cracks on the permanently exposed where the people would be walking, but the diaphragm would not be exposed. That back of this would not be exposed where people would not see it, and that's what he's referring to here. When compared to the other to be embedded diaphragm face. When compared to the other diaphragm face, see that? Just leave out that. And to the other diaphragm face, okay. It is unclear how a change in, right, so we talked about that already. So being supported on the bottom of the shims. And then next slide, and again, I talked about that being weird. So now we do know how much of it's left, 3 feet of this structure's left. Wherever it landed, now we know how much of it moved over, or how much is twisted or flexed, 3 feet. Now here are the cracks that he calls spalls. Question. Yeah, really. Here are the shims apparently placed on the deck here, as I talked about. This is also in the OSHA report, both of these images. Now this is interesting. The total plotted as principal tension stresses from the 3D model are, so I keep screaming it's tension and not compression. And here we go. It's right in his damn report. I've been screaming it's tension cracks forever, and there's tension. So all those people over there in those other forums, you can see how they just, barking. They're just lacking skills. They're lacking knowledge. They're washed up engineers. The plot has the diagonal post-tension bars and members 11 distressed. Or they're like Denny Pate, doesn't have the ability to understand what they're looking at. The plot has the diagonal post-tension bars and members 11 de-stressed. You see this? When they're de-stressed, look what happens. Look at these stresses here. Red. Right about here, we see a crack in the back of the darn thing. I wish I could bring them up. Now it won't let me bring up the OSHA report. For some reason, I can no longer bring up the OSHA report. I get that. Couldn't load plugin. That's what I get. This is important to talk about this real quickly again, and I'm gonna go back to the report. But Denny Pate, that report that he puts out, seems like he thinks there's 2 post-tension transverse bars around here within the range, because he calculates like 580 kips of transverse, about 580 or 570 kips of compressive forces right here in the diaphragm area. That's outside the diaphragm. That's in the deck. I don't get that. But I will state this, that those compression forces can count, since they're all compressing like that, and this is already going down, those forces can flip and go in a downwards and help push the diaphragm splitting down the middle. But it didn't happen that way. I don't see it happening that way. I'm totally amazed by the, right here is where it cracked, right about here. I'd love to see the crack, the end of this structure, where they don't show this side of it. I'd like to see it cracked, sort of like if we're looking at the face of it. Top view, something like this. So here's the center of the bridge, and like that, and like that. That's a total exaggeration, probably more like this and like this, not just straight across. I don't see it cracking straight across. Just a straight crack. It's got to have a slight step between, say if this was straight across and this is the center of the structure, I'd love to see the end of it. I think it's going to be tapered somewhere about from here to maybe the other post-tension bar here, and from there to there. And how I say that is I've broken a lot of concrete by putting loads on one end. And it breaks in the center. The forces still make this concentrate down the center of the structure of the concrete. but I always can find a taper going off left and right from the center. The center being the furthest point out, and then a taper always happens. And it's always, so if the load was here, the taper would always be that direction. I always find if I put a load here and break it, it would be here and here. In this case, it seems like this is more of a load on this end. So perhaps in this case, it would be from here back to here, and from here back to here. Very importantly though, either one, that taper, I would like to lean towards, that's the direction of the most loads. So yeah, I know it's a little bit of deck left over here, and you would say, well, by default, it's got to be this end. Well, I don't know that. I don't know that. And that's a cantilever that I do it on. This was a mid-span, so it's a different animal. It's a different animal. You want to see some shear crack in there too, like a little diagonal, 45, so that would help us out too. But let's go to back to this. So there's the cracks. Here are the cracks that this 3D model is showing, and he can't figure out what's wrong. There's a crack, and I can't go to the report, but you guys remember my video. I can't go to the report, but right here, there's a crack that shows up. And it's called tension. And that's what I've always referred to it as. Look down here, that little red, I want to call it, I no longer call it a chamfer, and I want to call it a gusset. I want to refer to this as gusset, and this is a gusset. So this gusset has a crack here, and this gusset here, we see the cracks here with the tape measure going round and round. If you guys look at the tape measure on the other side also. And it goes up this way, not so far inbound. It goes up this way right next to the edge. I wish I could load up the report again. You guys can look at that and find that. It shows in this 3D model, once you detension number 11 right here, it shows in this 3D model, look, the failures. Isn't that amazing? So if he'd have ran this before they detensioned, he would have seen the loads change. He would have seen that this spalling, as he's calling it, would have all identified itself. Something's going on over here that we can't have access to, but we do have this. And that red, you know, where it finally breaks, where we see the steel reinforcement. Look at that. Isn't that in line with that reinforcement? Man, I wish I had access to show you the darn the copycat of this, the version of the OSHA report. I don't know what's going on with my plugin. Give me your comments real quick. I know, Luna. I got you. I got you. I got your message. Yeah, he calculates 950 tons, 950 tons. Okay, guys. Yep, they calculate 950 tons. All right, so back to this. So this clearly lines up with the cracks of crack like hell. These guys. So he had it. He had the report, but he just called this spalling. He's right here where he question mark, spalling here and here. But ignoring the cracks like hell back here. Yet he made a statement very clear that if this was to fail, the longitudinal cables would fail. That you just made a statement that if this fails, the longitudinal cables fail. If the longitudinal cables fail, the bridge fails. So how can you, in good conscience, think that this is stable and strong? And how can any of them? So I'm triggered a little bit. Let me show you that again for people jumping in again, where he states that it must, the must part, up here on the left. Making it very clear about the must. So I think I might title this one Arrigoni also, guys. I have a motive to get that out there about the Arrigoni Bridge. And we're going to get that out there. So, you know, this is, okay, how about, I got to really think about it. Give me a second here. The total node must, there's not an option of may, should, must remain attached to the diaphragm / deck. And this is what I kept telling you guys, that this number 12 is a clamp force, is barely holding on. There's the shape of it, and there's his 950 kips showing up. So everybody who states 950 kips, Denny says the same thing, plus or minus. But his Denny Pate's meeting, it does not look like the fracture, the failure. The failure doesn't look like this, guys. That crack is way out here. This line is here, and it comes down and then goes this way. It never makes it like this. So don't think you're looking at the same one-to-one thing. All right. So must remain attached to the diaphragm deck in order for the longitudinal tendons to capture the longitudinal force component of the strut. Now, he does say strut. And then is the whole thing a strut, or is he just meaning this? Nevertheless, if this fails, that fails. If this falls through, the longitudinal cables fail. And we already know that the loads are, he obviously knows that what he's looking at with this red, diaphragm, and he held out. You got to figure, at least I believe he held out. He presented those images. He probably had a lot more to figure out and said, I know just what I'm looking at. I theorize, I extrapolate. I don't think that was all of the images he had. And we're not looking at all the images. And he said, yeah, this is why I can state this statement on the must. Because it might be other things to show the next stage of it is collapse. You know, cycling through his software, it says next you get failure, you get the bridge on the ground. I'd love to see that software. If he ran it, they should have captured his criminal investigation. They should have taken the computer, and they would maybe see what he ran. You know, did he run that part of his program and show it to go to failure? All right. We talked about that shear and compressor strength. It's up here. I want to show you somewhere about his statement. I talked to you guys about this. The moment created by the distance between the tension and compression forces must meet the demand moment. So when you're trying to locate your steel and reinforcement and all that, that it should be right there is what he's just stated. It's got to be perfect. You know, you can get it wrong by increasing the strength of it, as long as you don't crown it, you know, make a negative moment. But but you can't be too far away from it, or it's too late. The cat's out the bag. You're already cracked, and you're trying to pull it back. If you follow what I mean, that's just what the bridge did. It was already cracked. It was already failed. It was past this moment, and now he's trying to put it back into there with tensioning, post-tensioning in the bars. That's just ridiculous. The moment's already exceeded at this point. It's already failed. It's already a crack. And I mean the technical term for crack. All right, so and then we're going to talking about the beam theory, the loads coming down. But let's go above that and above the there's all this tangent stuff. I think I can't read it. 230 something kips, whatever, 475, but he's got it all doing what? If you look at this, what does this say? 950 kips. So put a comma there and put 3 zeros on it. And divide it by 2, and there's your tonnage. So 950,000 pounds. Look where it's going. He's very clear about it. Arrows down here. So everyone else talking about that it's going, number 11 is doing this pushing. Well, I don't know how it has the ability, number 11 has the ability to push off this much load, off this much load onto this, now what he calls a beam, yeah, beam, right? A beam theory, right? Beam theory. And I call it a girder. I called it a diaphragm girder. He's calling it just straight up beam. I just called it the two things because it's acting like a diaphragm and a beam because it's got two forces. It's got you got multiple vectors going on, right? It's got the post-tensioning pulling. It's got the, and this force is coming down. You got some going that way and some coming here. I can't make this out. Obviously some J-bar and whatever it is. This is the bottom of, I believe the shims might be down here. I don't know what this is out here. I can't figure out. I'm looking at the top view or side view. Oh, it says view something, BB. I don't know. So there are all those damn kips coming down. This is that shear crack I told you in the back. That's why Danny Pate argued against the OSHA report stating that, no, your assumptions are wrong, is what he was saying. Well, I agree. I think that it's no leaven pushing off. As I showed somebody yesterday, because this quite triggers me, obviously. I said, look, put your hand on my knee, and the person did. And I then put my hand on their shoulder. And I said, now push my knee without moving your shoulder. And they already had the hand extended out. And I said, now push my knee without moving your shoulder. And I made them make a fist. And it was not possible. You got to move the shoulder to push my knee. And just like this, you can't push out 11 if the shoulder is number 10 and 11 node, the top deck canopy. You can't push it. But these forces, that's why I can automatically say that, no, it's no pushing going on there, but this, and plus the cracks. But this is exactly what's going on. Here's the shear forces downwards. And I love how he defaults blaming it on that, but this is just stupid. It doesn't exist. This is already cracked like hell. You can't use those numbers. I can't give you a bunch of broken pieces of concrete and tell you I got a sidewalk. Mild steel, whatever, bending stress. Oh, that's right. This is his, how he determines that below. Without using post-tensioning, I think he just uses the mild steel calculations. Yeah, so that's all he did. Concrete shear strength. So cracking of the reinforced concrete element would be okay. Yeah. All right. So he's talking about concrete shearing there, and there we're talking about it right here. Flexural moment and flexural stress. Okay, well, I guess even though I'm saying shear, because I'm looking at his writing here, and he's saying flexural cracks. Well, I see it as shear also. So I think he's got, some weird stuff going on there. That's a shear crack in that capacity. Flexural's up like this. It's just sort of straight up. Going like that, you're in shear. All right, so and there's his loads down again. I can't read it. 475, is that half of 950? Is that 475? That would be half of that 950, but you see what's going on again. He's got all those damn loads going into the canopy and then coming back down. Hell, he's not even counting any, he didn't even do a discount for the deck. It's already sitting out here. We know it to be about, like you said, 950 tons. I think it's 930 something, 32 tons. If I use their 6 to the power or whatever formulas they use here, I come out with like 932 tons. And I said I wouldn't do math on this, but there's your math a little bit. Because what's the point? What's 18 tons amongst friends? So 950, 475. Going down, and he has it apparently. I think he's extrapolating. I think he doesn't mean it's like 950. Maybe he does, but because it's ambiguous. But maybe he's just saying it's 475 balanced down here. It's not. It's symmetrical, a total 475. But I don't know, because you go down here and you see 950. So I'm trying to work on this 950. Oh yeah, this is 475. Okay, so is he trying to say it's symmetrical, 950 total, and somehow he's got a tension moment going that direction? Is that rotation where you see the tape measure higher here and lower there? All right. I don't know if the T stands for tension. There's no clarity on each one of these things here. I think it is tension though. but I'm just giving you my bias on T. Clearly, he can mean something else in each one of his. He can change his own damn definitions. All right, so he's stating it's equal loading on the 4 shims right here. But we know if you look at the detensioned, it's not equal loading. That red is down here like this, and the red is down here like this, and you got what he calls spalling here and here. So let's go ahead and go up a little bit further. We see that that's what I talked about when it's inside the deck. So this is an as-built at this point. If he's sharing this image and along with OSHA sharing it, I would consider this an as-built. All right. I mean, you know, for our purposes of YouTube. The only notable difference from the casting is that the temporary post-tension bars and diagonal members 2 and 11 needed for the move were de-stressed. That's notable, very notable. A study of the local effects of this detention has been made and will also be discussed later in this presentation, which we talk about detensioning it, and it's going to be the images down below. I'm just working my way back up. Similar support conditions. All right, so we're looking at top view. That 1 foot thing, this time it's blue instead of yellow. The difference being that the permanent bearing, okay, right. The span over the road is supported at similar locations as were used in the casting area, but they're not. Similar is not. It wasn't like that. It was fully supported apparently over there, not. The difference being that the permanent bearings, meaning location, at the expansion joint south end. So the permanent bearings at the expansion joint south end, and EJ is usually expansion joint. I hope it's EJ expansion joint here. So, you know, I got it wrong, sorry. The 4 shims, rather than uniform contact pressure at the pylon north end. Oh, this is another bullet point. The 4 shims at the pylon north end, and then between there, rather than uniform contact pressure. So this is a giveaway. Remember I said everybody wants to tell you the truth? This little statement here is stating that rather than a uniform contact pressure. It's like slipping in there, like, what did you just say? You know, like small print. Oh, well, this means that, yeah, on the when we had it over here in the temporary casting area, we had it uniformly, that means fully supported under here with no, because we didn't have shims over there. We had it fully supported. Here it is here, uniform contact pressure. The 4 shims at the pylon north end. I'm slipping there, small print. I mean, it's real fast talking. Uniform contact pressure. Like, what did you mean? And so you see there's a huge difference. So then when you detensioned it, this caused this to go totally the 475 or 950 kips, whatever one you choose. It created that shear down here. And that's your crack. I mean, it's simple as that. And it's simple as that. There's the fully loaded, but we can't get a photograph of it. During this time, the pylon end diaphragm was uniformly supported over its entire surface area on the original soffit used during the casting. So right here, the entire surface area was, and I said that's a question I need to answer. Well, here it is in the damn report, right on page 10, apparently, page 10 on my screen. And also, no significant cracks or de-stress of this region were noted, So specifically of this region that he's talking about under there. So that means cracks are everywhere else, but he's not, this is the way you get around, you know. I specifically said, oh, there, I didn't say that you thought that I meant nothing else was cracked. I specifically meant that. Okay. Full post-tension, etc. It doesn't talk about being grouted here. For several weeks prior to the move, during this time, the pylon end diaphragm was uniformly supported over its entire surface. Entire surface, guys, that means the entire surface on the original soffit used during the casting. That's the whole thing, man. If that thing was fully supported there, maybe this would have given us more time for the bridge to fail. But I already think it was creeping because of the cracks and what I call now the what I call it, no longer the chamfer, but the I just said it a few minutes ago. The if anybody can comment and help me out. The plate. Damn it! I said it earlier. The methods and results of this independent evaluation will be discussed in some detail further below. Independent evaluation. So when I stated maybe Denny Pate could argue that it has been independently evaluated because he presented it before these engineers, and these engineers didn't say no, didn't run him away. Now I get to say that nope, since he's already made that part of his presentation, if this is a photograph, then he's stating that he had an independent evaluation before he presented. Before he presented, as he's presenting this and beforehand, as we see here. Tuesday morning, after about an hour of review and evaluation, FIGG had conducted sufficient supplemental independent computations to conclude that there is not any concern with safety of the span suspended over the road. It says FIGG had conducted sufficient supplemental / independent. How do you get that? Because it didn't say FIGG and someone else, but we know now that FIGG was out there with one other person, but it didn't say FIGG and someone else. So that is weird. And maybe he had a mouse in his pocket or a cell phone that he used to contact. But what do we have here? The recommended temporary shimming region is shown below in blue. This is what Denny Pate wanted shimmed. The entire capture, vertical load coming down of 12. And the diaphragm area. Down. Nothing back here saying stop it from kicking out. It was a vertical load he was trying to support. All right, so that's 100% clear there. It's the vertical load under 12. It's not the shimming over here, shimming here, here, or over here, or in the very front, as I've seen other people try to claim. And not over here. It's not just the back end of this, it's the entire 12. He's trying to stop it, the beam he calls it, and I called it a girder, from deflecting in the middle, from having a moment in the middle. Which is contrary because he just states in his whole entire report that this is sufficient, that there's no moment taking place. There's no, there's no deflection taking place. We're just looking at spalling. All right, cat's already out the bag. It's already failed at this point. It's cracked. All right, so shims placed on the span move were, and here are the shims. That's just for identification purposes, giving you data. And I'm going to run to the bottom of this. Here is where people are getting confused, but here we go. Immediate action. Tuesday morning, upon seeing MCM's information, FIGG requested that as a prudent action, MCM immediately install temporary shims directly below the nodal area of members 11 and 12. That's the entire diaphragm area. And the top of the pylon pier, while further evaluations were going on with FIGG. So he immediately said, put shims under there. I don't know if they did that. We saw the shims crack like hell. They were crack like hell shims. I mean, crack like it was photographed from the top, the spalling they identified. The shims appear to be sitting there. So these shims might have been put in place. And that was, you know, like I said, the cat's out the bag. It's too late. This is where I think the issue went wrong right here. We tension decks D1 and C2, C3. D1 and C3, but they weren't grouted. And then they moved on to 11 and 2. And then they moved on to the next. But they weren't grouting it beforehand. The loads were, I already went down that in other videos. See, talking about bending moment. This is in his diaphragm. Not talking about shear happening of the 11 pushing off 12. We're talking about bending moments here. and it will reduce the load of the shims from the current values, right? False works. Right. When the false works of the CI of the span is removed, will reduce the load of the shims from their current values. So some people interpreted this is the counter force he was going to use to stop it from sliding off. No. No. All right. Jumping down to 39 again. And now I should be wrapping up. Very important. It is unclear how a change in distribution of the contact pressure on the bottom surface from being supported like this for several weeks, so like this, being fully supported, as we know, as I just showed, to now giving it some, point loading now, and then releasing the load, the clamp force in there, and you wonder why it failed. And he says to being supported on the bottom on the 4 shims, just 4 shims, could possibly create these top spalls. He's just totally, how could it possibly do that? It's unclear, he stated. Well, you detensioned. At the moment you detensioned, you allow those 950 kips or 475 kips, whatever you're stating, to go right down 12. And your own statement tries to say that this thing can support any page statements that the diaphragm can take the loads is obviously false. I'm sorry, he calls it a beam. Using your own imaging, your 3D imaging, you see that it shows that once you detension, right here, number 11, specifically that would be B, the top one I believe is B, the bar, that this would be created. I would love to see the images after this. What happened next? What's the Rex cycle of images? Collapse, I bet. And there we go here. And that's the vertical cracking. And these forces are very interesting. And look at the forces here, increased in the transverse cable on the outer. The forces got really loaded. On this, I want to see the rest of it, how the rest of the transverse cables, how this software interpret the forces once 11 was removed. I'd like to see the rest of those transverse cables, specifically where it cracked, and also the friggin' canopy on the red. And then this all of a sudden is contrary, because now this is total red. Maybe he changed the colors to mean something else, because you don't see red here. So my guess, when we're looking at this, the color pattern, he's changed his color patterns to mean something else. The change principal stresses solely from distressing the post-tension bars, number 11. So maybe 11, that red now means stresses, which is amount of tension. The analysis, neither total stresses nor post-tension bar only stresses. Okay, so to leave this part out, that's this part he's trying to slip in, and then read the rest. The analysis shows any spike in tensile stresses at the corner of the deck / diaphragm number 12. Okay, let's locate this first. The tensile stresses at the corner of the deck / diaphragm number 12. Corner of the deck. So I don't know if he means out here, because the deck goes out to this thing here. So the corner would be here, maybe. Then let's put this in now. Neither total stresses nor post-tension bar only stresses. Neither total stresses nor post-tension bar only stresses. Change principal stresses solely from de-stressing the post-tension bars, number 11. All right, so 100% remove the number 11, right? And 11 is a deck released, and also the back of this. I don't know what this color scheme is, but this appears to be the deck. Some weird version of configuration of what it's showing, I have no idea how this works. Looking at it, this is all solid now. It doesn't really, take the right form. This looks like the diaphragm here, but then what the hell is this? What is all of this? An anomaly in the software, but nevertheless, it's more focused on this perhaps, and this is all, maybe this is the way the software works. And he just focused on that when he asked for it. The analysis, neither total stresses nor post-tension bar, only stresses. Okay, so no post-tension bars. Shows any spike in tensile stresses at the corner of the deck. All right, so he's stating it doesn't show any tension stresses at the corner of the deck, which is, again, I don't know where the corner of the deck is. Oh, maybe this is the corner of the deck, and now here? No, he said 12. So that would be here then. I would say corner of the deck is that extension. So here and here, and he's trying to say shows any spike in tensile stresses. All right, so spike meaning change. It didn't say it didn't show any. It says spike. I think he means here, and then he changed the color patterns. So here and here, which would be here and on the other side. That so bothers me. I want to show you the other side. Give me a minute. So here, the corner of the deck, that's the part that sticks out right there. The tensile forces he's referring to that doesn't show a spike, meaning it doesn't show a change. He's doing trickery on his wording. He didn't say it doesn't show any stresses. He said it doesn't show a spike. And what's his definition of a spike? More than 20? More than 100? Well, it's subjective, isn't it? He's using words that like spike. All right, so you have to use your own brain on that and realize you're being bedazzled. All right, slide down. Conclusion and recommendations. The diagonal type cracks in excess of F-dot criteria. So he's stating first he doesn't know what they are and they're nothing. And now he says they're in excess of F-dot criteria. Should be sealed with approved, some correct, diagonal cracks, approved method and materials, epoxy injection, etc. So the spalled areas have not been replicated by the engineering analysis, however. Understand this. This is so critical that he says the spalled areas have not been replicated by the engineering analysis, however. That means himself. That means the computer. So let's go back to the very critically that he's stating he can't figure out why these spalls exist, but yet he's calling them spalls. You can't call them spalls if you don't know them to be spalls. They could be, spalling. Yeah, you can call them spalls. You can call them spalling from, from the forces from the canopy caving, bowing down, bowing, and also the diaphragm, the deck bowing, causing the canopy to pull over. And this is what's so crazy though, that they can't determine those spalls. Undetermined. That they just magically existed. And that's what I find it crazy, that they're going to give this guy a $40 million contract to evaluate a steel structure, and he can't even evaluate his own structure. The spalled areas are minor, and is recommended that, how can you say they're minor? You see the conflict? You just said you don't know how they became about. But now you just said they're minor. And it's recommended that they be prepared using normal procedure and poured back along with the upcoming pylon diaphragm pour, quotes, quotes, different from any prior to the back spanel and false works pours. So just ignore them and just put them back together. I don't know. It doesn't sound like, it should sound like some contractor would say this that has not a clue what's going on and just says, hey, just patch that back, just patch it. And actually, I don't know a contractor that would say that. I've run into some bad contractors I don't know one contractor that would say this, would look at that and say, let's just patch it. You know, that I don't know what it is. Let's just patch it. I don't care. With all these engineers available, I can't imagine with that, you know, being keeping things relative. All these engineers available, I don't know a contractor like MCM would, hey, let's just patch it. But apparently that's status quo up there. That's the way they go. That's the way they roll in Florida. Just, you know, engineering's not needed. All right, so hey, Mark. Hey, Danielle. So let's find that part where Denny Pate talks about that distance here. I think I should find that for you because I stated that. So let me race to the top. It sounds like he's stating there's 2 bars in there. And if you remember the OSHA report, he kind of went on about that transverse bars and how they were not in the diaphragm, which I stated. I think with Mark and I stated that together, and he mentioned it. But Denny Pate. FIU requested a progress meeting to be moved to 319. Progress? Wow. So FIU clearly wanted progress to continue. I'm going to show you. I'm trying to find what I stated. That he talks about, there's the loads all down 12, where he talks about the transverse, and it sounds like the transverse is helping capture, but an extra one that doesn't exist. I mean, that's what I'm kind of biased against right now, that he might be stating. Let me see if I can find it real quickly. The flexural stress is on the bottom of the transverse diaphragm beam. The field operations are conducted with the intent of achieving reasonable equal loads at the force shim location. Reasonable equal loads. It's placed to comport, you know, in symmetry. So yeah. Assuming that was achieved, the span weighs 950 tons. That's total. Flexural moment. Okay. Let's see if I can find it. Transverse. See, this is what I find. He says that, you know, the shear cracking should be would be expected. I find that, you know, very very telling. Why would you, if it was expected, you would not, you would cancel it out, as he shows in his own formula up here, saying, hey, we have to cancel out any tension and compression with reinforcement. Why would you allow your bridge to crack? That's ridiculous. He states right here again, it would be expected. So cracking of the reinforced concrete element would be expected, as allowed by normal reinforced concrete design methods. Yeah, shear cracking, right? It would be expected. Nobody likes shear cracking. So there's again 950, 475, 475, showing symmetry. That's that equalness, if you will. You got 950, got it all on one end. Oh, 950 tons, right? So you got it half on one end. Strut and tie tension force, right? This is interesting, 50 and 30 degrees. That's at 11 and I don't know the other one. Is that 10? We'll come to that. See that there, the very important. Very important. Hold on, let me show you something here. $50.87 degrees, 30.884 degrees. 51.92. That's this one. That's 10. And we noticed to be about that 30 degree, right? 30, whatever degrees it is. So, you know, it's hard to figure out from where he's actually pinpointing himself at here. This strut and tie tension force. You know, is he talking about 10 and 11 at this point? The loads down them. And, you know, and there's his T for tension, as I told you guys before. I think his T consistently tension on this guy's paperwork, capital T. Remember, capital T. Yeah, I don't know where this is. You know, it's so, I don't know if it's written in here somewhere. You can't really read that shit, or are we just missing a page? Or maybe I just missed it. All right, so moving down. I want to show you that transverse cable, though, the transverse one. So he's using half a theoretical weight, the span right here. That's where you come with that 470, 950. Good, yeah. You can see he's using that half weight when he does the 475, that theoretical half weight. Because it spans, you know, halfway across. You get this, halfway across, the other side gets it. It's the way it works, unsupported spans. I've talked to you about that in other videos. But he's using it also. All right, area of steel tie. Now using a full amount, this is like a factor. So using the full, and usually it changes to 0.9 down here. Where's the damn transverse? I love how he says, okay, just him checking off himself, saying, yep, I did my math, okay. I use a check mark, actually, but yeah. Bending check beam theory. All right, so we talked about that. Where the hell is the transverse? It's right here. So there's all that load he's saying there. I don't know how it's creating a moment, though, if it's so balanced. So I don't get his rotation moment. I don't get that at all. Unless he knows it's already, that this thing's already sheared and cracked, and he's using the calculations of the tape measure, knowing that it's now rotating. Bend check beam theory, right? Where the hell is my transverses? Right here. See, the moment created by the distance between the tension and compression forces must meet the demand moment. So if he's stating this, how can he, above what I just showed you, state that the shear cracks are okay? Well, why didn't you just meet the demands, knowing that you knew that it was typical and to happen? Why didn't you just meet demands and stop the shear cracking from happening? Why would you allow that? Cracks are total failure. I mean, you know, fibers can sometimes keep you 30% before after they fail. After you're failing, your toughness is called. You might be able to last 30% more before total failure. Yeah, and I told you that was no go for me here. I can't read this. I can't read it. I can't read that. Can't see it. And then A's down here. I try to follow, but then I couldn't figure out where A was. What A was. And then your tension and compression. And I'm like, wait a minute, what's this? You know, I can't figure out where this goes. I know there's 2 foot here, but this I couldn't figure out which. This appears to be D, depth. So this would be the 4 foot, and then I have no idea what's pushing here. Bending check moment, you know, I'm like, the hell? You know, why is it sideways like that? I can't. That one's got me. And then you got the measurements, 3.24, 3.0900s. I lost, but nevertheless, he came out all this. I didn't read it. Came out with everything passed. Everything was okay. And remember, he's basing this on a beam that's okay, not with cracks in it. Not what he doesn't even know what's left of the damn structure, and he's basing it on that. Here it is, 2.4 by 8 foot. Right, there we go. The shear and the 2 shims on one side is approximately 476 kips. So remember, 476 is the same as, I know it changes just slightly. I don't know why he didn't stay consistent, but this is 475. And now it's 476. I know it's like, you know, it's hard to read. Here's 475. There's 475, 950. Now we got 476 coming out. I'm like, where the hell did he get 476? And now we're, well, I'm like, all right, whatever. Let's just go on. 476 is only the, this looks, now it's, I think that might be 476 now. So it went from 475 to 1,000 more. 476. Now you see what it's like trying to read this damn report. Now we're at 476. Thus, the average shear stress on the vertical load is approximately, and I told you we went over this, and he said it was okay. 8,500 pounds per square inch concrete, per square inch. This is per square foot. So you do that and you're at 100 and like, I think I did the guesstimate on that for you real quick. Let me do it real quick. About 140,000, and here he's at 60. So he's stating why the diaphragm can take it. Why it can take it in 1 square foot. I only did 1 square foot. I was apples to apples, and he's got this down to the vertical load is approximately 60,000. So 476. I don't know how he did that. How he came to this. That doesn't seem like it works out to me. If it's 476,000 going down, but he ran it on a diagonal, I guess. His shear force is coming down from 12. I think he took some liberty and decided that he can use the 45 rule pretty much to call this all the distributed load of 476, and then came with this number. Because clearly, if I just run 476 down, what was the number? 2 foot wide? 476 down 2 foot wide. I just half that. I'm at 238. Well, I'm only at 140 here. So I'm not making it. I'm coming up shy by 100 and something thousand pounds with the way I just did that real fast off the cuff. And he's only got it at 60,000. So I'm like, huh, how does that work? How did he do that? How did he put the load down at 476, which you guys see there? But then he changed it to, thus the average shear stress from the vertical load is approximately, and if you do it, the answer is because he did 8. 8 times 6 is 48. See the difference? But the true load path is as he's showing up here. This is, I mean, I don't get how all these engineers were here and didn't bring this up going, wait a minute, you did that one, but you clearly show in your drawings the load path is different for that column. In fact, you say it's got to be fully supported, so the load path is in the friggin' air. You got it on shims now. So you can't say 8 square feet. Let's back that up. You can't say it's on 8 square feet because it's not on 8 square feet. Let's go to the 8 square feet so you guys can see that again. 8 square feet is the bottom. The diaphragm's 2x4, all right? Diaphragm's actually larger than 2x4 because you also have to count the 1 foot square, the 1 foot by 2 foot of the back of 12. So you count the back of 12. So I showed you that. I think that's the angle there. But you count the back of 12, and that's like another 2 feet you get to distribute the load. But it's kind of a point load deal because that's coming down that damn column. And then you got to transfer it. I mean, he's disrespecting it as a column. He just has it. Okay, that's the backspan. I think Danny Page just lost it. You know, my own thoughts. I just think he lost it. And these skills he had, if he had them, I don't know if they, you know, his calculations remind me of just common, simple errors. So he's got 8 square feet here. Well, it's on shims. All that comes down to your shims. And if you want to make it transfer loads to the shims, well, you got to think of it like a cantilever and unsupported spans from shim to shim, and especially between number 12 and the 2 shims to the side, unsupported spans. And then you got to figure out whether your beam was designed to transfer the loads back down only 4 points. And they were not. None of the structure was designed to transfer down 4 points. So 4 shims. So this is just, you know, this is just junk. This is what I said. It's just junk. This is just bad calculations. It's just shit. You'd have to do this and then put it down into 4 shims, but you couldn't discount that friggin' 12 is sitting off there with 475 kips. He's stating that per that statement there, and all these people, all these engineers here watching, he's stating that the loads coming down here are transferring down these shims, but he's stating it's transferring down 8 square feet. We know that's not true in that statement. It's an untrue statement. And here's 475 and 475. And per his thing, it's half the structure, 950,000 pounds, but he changed it to 476. So he's stating 476 is coming down, not here. He didn't put 476 of arrows on his diaphragm. He says they're coming down a damn 12 column. If that's the case, they got to transfer to this deck, to this diaphragm, this beam, or girder as I call it. So it's going to do that. It's going to do this, and it's going to want to punch down. And there's your shear that happened. I mean, it's clear as day. Now they're going to give this guy $440 million, and he can't evaluate his own structure. He can't even see the fallacy in his own presentation. And all these clowns that are there couldn't see that this shit is just shit. No one spoke up going, well, that doesn't make sense. So the diaphragm cross-section area is approximately 8 square feet. Next sentence, bullet. The shear from 2 shims on one side is approximately, the shear from 2 shims on one side is approximately 476 kips. On one side, he's now 2 shims. I don't, you know, so on one side is 476 kips. And then the other one would be 476 kips. It's symmetrical. Symmetrical. But he placed it on there. 8 times 60 is 480. So, yeah, bullshit. If I'm looking at that wrong, I apologize. Nodal shear transfer vertical loads. Okay, we're back to this stuff again. So this is that 12, the nodal, the 12 shear. He now states that he's canceled out stuff and blah, 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 blah. The shear friction transfer between the diaphragm and the nodal region. Trigger myself. Nodal shear transfer vertical loads. Here's the vertical loads. And there's inch square, blah, blah, blah. You know, it doesn't matter. There's a 60. There's a 60 again. It doesn't work out because it's all based on the wrong calculations. It's not going down that path that you're stating. It's not going into 8 square feet. It's going in an overhang down a column. I mean, it's a friggin' column. And the column didn't have a way to distribute the loads over to the full diaphragm. It didn't have like a steel bar underneath of it designed with no deflection with 475 kips. That's just a thought for you guys. Okay, nodal shear transfer vertical loads. And there's this factor of 0.9, 1504. It's up here too. I'm not going up there. And then easily okay. His own statement, confidently stating it. Okay, total near shear, we already looked at that, and this obviously is wrong. It's like this in failure, true failure. And then the must part. I'm gonna end it with the video, ending the video now with this stuff. The total node must remain attached to the diaphragm deck. This area here must remain to the diaphragm deck in order for the longitudinal tendons to capture the longitudinal force component of the strut. Oh shit, I never found the number showing you guys the damn thing. The where he states that, see, these looks like the transverse cables right here. That's the transverse cable. Somehow I think he calls it 5 foot. I have it like at 4 foot. And that's counting the outside here. So he's stating that that's the transverse again. That for this not to fail, you can't lose number 12. Can't lose it. So everybody says it's a zero force member is obviously, you know, can't understand what they're reading, and I don't know. I now know if they're idiots. Rebar cross assumed shear, right? Okay. So this is the mild steel that he's trying to prove that the steel is okay. Here it is. Transverse post-tension bar confinement. Transverse, that's the front going across the deck. There are 65 4x6 0.6 diameter tendons and the 175-foot span. Those are transverse span cables. The total transverse tendon force is approximately 65 times 4 times this, equals 9,600 kips. Or 9,600 kips divided by 175 feet equals 54.80 kips a foot. Well, this, he divided by 175. The problem with that is the transverse cables do not go the full length, so you cannot divide by 175. This is another, you know, childish mistake. This is like, you know, you fail the whole class mistake. The bridge, the structure does not have transverse cables via 175 feet. You have, it stops. Here's your last transverse cable right here. That's 4 foot, 1/2 inch to there. I don't know if the 175 is measured out to here. I don't recall, but let's just say let's just call it right there. That's 4 foot. And this is 4 foot, 2.5 inches. So we take 8 feet off of that. 8 foot, 8 feet, 3 inches. 8 feet, 3 inches. 8 feet, 3 inches we take off. And now his clamp force has gone up because now it's not just 54.8. He gets to take 8 feet off of this. This number can now changes, but he only gets this clamp force of this he's talking about, 54.80 kips. He only gets that to state that within this range. He does not get to state it in the diaphragm. The diaphragm is 4 foot tall. He does not get to state that. It's got 2 foot in this case. Oh, this is like 3 foot diaphragm down here. So down here it has 1 foot that these, so it's got about right about there. Yeah, right about there's the diaphragm, I think. See the check, the dot, 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 dot? That's probably the diaphragm. And that says 6 inches. So it's got 6 inches to make it onto the diaphragm. It's the deck area that can't, but interesting enough, the underside of this deck does have a nice chamfer, which would really help in that support getting those 6 inches. And the same here, I got to give him some deduction for that, or give him some credit for that. Not credit as in support, but credit. There's 6 inches here too. I think that's that chamfer underneath of the underside. So, but you get 2 foot down here. So there's 2 feet. So as I keep stating, the north side and the south ends are nothing alike. I know in those other engine tips forms, those guys are so brilliant. I'm being facetious. They're not brilliant at all, even comparing these two. They're nothing alike. The OSHA report comparing these two, they're nothing alike. They're nothing alike. There's 6 inches before you get the stability of the diaphragm. On this one, the transverse cables have to do the work. Being this is 4 feet, and 2 feet of it is diaphragm, and we're giving that little 6-inch chamfer there. You got about another 2 feet before you get to this. So you got 2 foot of cabling that has to carry the load by itself before making it onto the diaphragm, before making it here. And that's 4 feet total development. And these things were only designed through their repeating process. 2'8" to 2'6", so you guys know it. They're not all consistent. They're 2'6" and 2'8" is what I've seen. That these things are not just not the same. They're 2'6", 2'8", 2'6", 2'8". You know, it's not an easy one to follow. It's so you don't get to call it per square foot because it's got kind of a weird setup. Those 2 inches, kind of a weird jog. And so he gets to say that this part of the deck has that much compression, but then this is now unsupported. These guys are taking the load at this point for 2 feet. So this is a whole nother dynamic down here. This is a whole nother calculation you have to do on your own. In other words, this part, it's just nothing. It's like, okay, well, that's nice. But specifically the diaphragm area, which would be the failure part, would be from, well, we know this fell from here. This 11, 9, 10, 9, 10. 9, 10 nodal area, right about here somewhere forward. So you want to know all of this. This would all you want to know what's going on here, but specifically right here. How the hell do the loads transfer? What happens here? How do these experience the load? Because they now have to act like a transverse cable also. They got to double duty a little bit. So this is just, they should have spoken up here going, wait a minute, this doesn't make sense. Your footage is wrong. There's none in the diaphragms. So you got to take 8 foot off of that. And then also the ends are different as far as they're not making all the way out. So these calculations are wrong. This is Denny Pate's calculations. The assumed node has a length of approximately 4.75 feet. The assumed node. 4 feet 9, 4 feet 7, 4 feet, quarters. 4 feet 9 inches. So it's 4 feet 9 inches. It says 4 foot right to here, but he's using 4 foot 9. So if I take off 1 foot and call it 3 foot 9, because I'm taking off a foot for this blister that sticks out right here. If I do 3 foot 9 from here inwards, I come up shy. I don't even make it to this. So I don't make it. I come up shy by 3.5 inches, if I did that right. I come up shy about 3.5 inches. I don't even make it to the first transverse cable. So his statement is, apparently I make it there, though. The assumed node has a length of approximately 4.75 feet. And the node, just for clarity, I looked at this. This node is this guy here. I think it's the nodal area that he talks about. But here, for clarity, his nodal area, if you remember the triangle, It's kind of a weird shape, and he calls it the nodal area. So this 475, I don't know how he comes up with it. He doesn't have it written down in any, it doesn't written down. Besides, he used the word approximate. Thus, the tendons provide, now he's adding the tendons in there. 54, he used this calculation up here, which I already proved that was wrong because he's wrong on the footage. 54.8 kips a foot, which actually would be a higher number for him to use, actually. And then he calculates this as 4.75 equals 2 sides, equals 520 kips of confinement. Now, he used 2 sides here. So, 270, 2 sides, 54 kips a foot. I think the transverse cables were tensioned out. What did they really do? But he has it now that the transverse cables are applying 54.8. He used the entire deck. There's transverse cables, he has it applying forces where they don't exist. So he has a transverse cable applying forces out here, 175 foot out here, and he has it applying forces, as I showed you, out here. They're back here, 4.5 feet. 8 feet off. He's got them applying forces where there are none. So this is 100% wrong. Just gets a big X. They're not participating at all in a transverse capacity in the diaphragm nodal area. 100%, this is a fail. They're not in the nodal area. There are no transverse cables in the nodal area. There's no compression forces to look at, confinement, compression force. No, this is nothing. This doesn't exist. Check big X. Big X. None of these engineers know their own friggin' plan. All of them speak up. They go, wait a minute, there are no transverse cables in there. The 175 can't work. You see how I'm triggered by this? And let's scroll down. So total nodal shear. So this means this is just trash. You don't have to read this because you already made some bad assumptions. This can't be true now because you made assumptions based above using these numbers. So trash. Don't read it. That's why I don't do numbers. I don't do these numbers like everyone else is chasing these numbers. They're missing the basics. That is not where he's stating the numbers are false. False. It's 50. You see it there? Just X mark. It's just, don't have to read it. You don't have to worry about factors or this loading and all that. You don't have to. They're just false numbers. Okay. The factor demand nodal shear. So then this would be this much. This would be false based on false data. This is less than either the factor values using that. And he's right. Okay. Using this formula. Note the upper limits for this formula here. It's a formula. Were checked and also found to be within limits. Okay, so obviously you're using the wrong calculation, so this is trash. Conclusion. Based on conservative calculations, it is concluded that the design meets the LRFD strength requirements for the temporary condition. Based on the conservative calculations, since the calculations are off, this is trash. And so that's just trash. The assumption's 100% wrong then. And since you believe transverse cables are here where there are none, this would be trash. But we'll look at it anyway. The three-dimensional volume element, finite element evaluations were conducted to understand. Right. This evaluation included the 4 shims location placed at the bottom. So now this diaphragm, this program he used the 4 shims. And we talked about that. Those are the way. And in this way it looks like with the 4 shims, it says it looks like that, which we know that to be true. That's about where the shear cracks like hells look like. This is with the 4 shims in place. So it looks kind of balanced, symmetrical. All the stuff looks symmetrical with the post-tension bar in place. Diagonal cracks, both hand and calculations, and the 3D volume element analysis concur that some of the cracks of nature, cracks of the nature photographed are possible. That is true because the 3D element shows the cracks before they duplicate them. Why the cracks did not develop in the casting area is likely related to having a substantial portion of the load carried in the central area. 100% true. When a detension 11, it dropped down. The 12 vertical loads dropped down, causing shear in the diaphragm, as he calls it. The beam theory. Having a small crack width on the permanent exposed faces, preferably. Yeah, you don't get to choose though, do you? But compared to the other to be embedded diaphragm, that is just a stupid ass statement just added there. That just says, what the hell was that? A wish? All right, it is unclear how to change the distribution of contact pressure on the bottom surface from being supported like this for several weeks. That's it. This is a scam image because we know that it wasn't like this means, as I showed earlier in the video, it was fully supported. And so it's not like this. So being supported on the bottom of the 4 shims, if you can't figure that out, you're a crackhead. You have crackhead thinking, I'm sorry. But Posse create these and already talked about it. And he calls them spalls, which he doesn't know what they are, so you can't call them spalls, I stated. And there's the crack, the 3D model with the member stress, de-stress number 11, shows the post-tension, shows the cracking, the forces in this. Interesting, the forces do go past the pipe in this failure. The forces go around the pipe, but they don't go here. So obviously they don't go here because of it figured out that somehow the failure. Remember, I kept saying there's 0 forces, and I showed in videos. I said there's 0 forces below the pipe, and there it is, 0 forces below the pipe per this model. And then this is a switch of coloring. Don't get crazy on that. Conclusion: the diagonal type cracks in excess of F dot. Right. So, that's my conclusion, is that, he knew that they had all the data. They could see that he had wrong calculations, that he was just dropping a ball, and none of the engineers, with all their intellect and skill and knowledge, they did not know their own structure. Yeah, I've been going at it for a year and a half, but I only looked at this tonight. Besides the first time I published it, I just found it to be just junk, and I just published it for you guys, and I left it alone. Just decided tonight to take a glean at it again, and then I'm seeing all these stuff pop out at me, and I'm like, really? Let me go ahead and do the video. And so that's why I made the video for you guys. And ultimately, I am going to send this to Massachusetts. I'm going to send this video to Massachusetts because I think they need to disqualify FIGG engineering. So Massachusetts lawyers and all that will be getting. You see the email I got. I mean, it was when they responded to me, that shit went around to a lot of people. And I'm gonna keep it confidential because maybe the engineer didn't, the chief engineer and lawyer didn't want me to see that part, but it went around to a lot of people who are concerned about what I'm looking at, what I want to look at here, and what I asked for. You should see what I asked for. It's going to be very, very, very nice. I'm still going to get it, and they made it clear you're still going to get what you're asking for. They made it clear, and I'm getting it hopefully for free because I'm doing it for the public, for you guys. But I want them to disqualify. I want them to disqualify FIGG engineering based on what I just showed there in this video with you guys. Hopefully you can appreciate that. And if you want them to disqualify them too, then please comment over there. Please disqualify them to there. They've already said that, you saw that, they've already said that they're going to they're holding their grounds with sticking with FIGG as the inspector for ARRIGONI Bridge. But there's still a window here. Who's eating funny mushrooms? Who's got the mushrooms? Connecticut Bridge, right. Hey, Doss. Well, the point load won't change, that's for sure. If you can calculate those shims, the point load will not change on that end. And if you use Denny Pace, and I like it, half the bridge structure, the weight, you then put all of it, you calculate all those loads, but each one has got a span between them. Remember, unsupported span between them. So you're going to have to point load them, but you also got to figure out how number 12, what point load is it putting on the diaphragm itself? And that's what he was attempting to do all wrongly. And then you go from there. And again, I don't know why he added the whole entire bridge on down number 12. You didn't have to. I think that's an error too, because a lot of the bridge deck is going into the diaphragm. It's not going down 12. He just threw it all down 12 for some reason. I'm like, really? So you're actually, by what he stated, it actually is implying that the canopy is holding up the entire bridge, is what it amounts to. And it all goes on 12. But none of those engineers saw that. Even the OSHA report didn't catch on to discredit him to say that. You're stating that half the structure is on half the end of the structure, 950 tons. And then you showed us 475, and he changed it to 476 and 476, is going down 12. I say that's not true. If that's the total load of 933 tons Barnhart style or whatever, Barnhart uses a German engineering company. I looked at it. They did the calculations. They farmed out